both. Okay.
Yeah.
Okay.
Yeah.
Thank you. But why is OpenSCAD slow? So here we have an image of a mesh rapids. So basically a mesh is like you model a solid by using triangles to capture its surface. So, but with solid mesh modeling, so we want to make sure that our mesh is not only a visualization tool, we want to do some solid analysis on it. So it has to be more than just a triangle soup, meaning that we need some connectivity information. So from a topological point of view, we need it to be close to manifold. So your surface is not supposed to have holes. And also your surface should be like a plane. So you don't want three faces joining together, for example. And from a geometry point of view, we want to avoid having self-intersections. So the faces should not go through each other. So, but this is actually not easy to implement. So if you do floating points, which is the first thing you do, you get into robustness issues because with floating points arithmetic, you don't really have the nice things like associativity when you work with real numbers or rational numbers. So this basically violates Euclidean geometry assumptions. So at the end, a lot of those libraries will produce broken topology, which is a major issue. And otherwise, you can also do the exact arithmetic route. So you store the exact rational number representation in memory, but this is slow, uses more memory, and you suffer from a problem called snap rounding. So basically, your model is perfect in that exact representation. But once you snap it into a floating point grid, then you introduce self-intersections. So you kind of cannot get rid of this like either topology or geometry problem. So in Manifold, we solve this by implementing Smith's robust inexact algorithm by carefully designing the floating point predicates to get a guaranteed topology even for random coordinates of input. So this is like the floating point predicates are careful, so they give consistent results. And then via combinatorial arguments, you get a correct topology. And we choose topology over geometry correctness. So basically, we will have some tiny self-intersections sometimes. But the reason is like we think that broken topologies is harder to fix in a reasonable manner. And some algorithms and data structures relies on this. For example, here we show like a half-edge data structure. So this implicitly assumes two-manifold representation. And also geometrically incorrect models are everywhere. And when you apply affine transformations, you get geometrically incorrect models. So we prefer preserving topology. So here's Manifold's API. So I translated the C++ thing into a more abstract data type. So we have the mesh Boolean operations, which are just union, subtraction, intersection. And then we also have some transformations. We have translation, scaling, rotation. And then we have warp, which are not affine transformations. So at the end of the day, copy Booleans and affine transformations, they are all lazy. So they build an underlying abstract syntax tree. And when you do queries, for example, you want the actual mesh, or you want to compute surface area, volumes, etc., they trigger the query. So it will actually evaluate the underlying abstract syntax tree. So this is very simple and intuitive, but actually this is the hardest part to push through, because when you tell this to imperative programmers saying that you can do lazy evaluation and things will be faster, they'll think that you are mad. So why pushing things to be evaluated later can make things faster? So actually, I did push this a bit. So we have some little benchmark to show them by lazy evaluation, we can do some AST rewriting, tap into some specialized APIs, and then it will become faster. And the weird thing is no other computational libraries, computational geometry libraries have this for some reason, even though this is like very trivial. So before getting into the rewriting, we have some notes about the correctness. So the problem here is like the mesh Boolean algorithms we have are not really associative or commutative. Mainly because we are using floating point, and also we are doing some mesh simplification after each mesh Boolean. So things are pretty much not The same if you do rewriting, kind of like floating point arithmetic. But we still think that it should be fine because users should not depend on the exact results. So for meshes, if you have a flat surface, there are many ways to triangulate it into triangles. And they are equivalent in some sense, but they are not bitwise identical. So we think the user shouldn't really expect this, which is different from floating points, because floating points, you have a specification and people expect your implementation to implement it. Our only guarantee is like, apart from the topological guarantees, we guarantee determinism. So no matter how many cores you are running it on, we guarantee the same results. And this has some implication later. So about the AST rewriting part, these are quite trivial. The idea is we want to maximize arity for Boolean operations. So because we can then use optimized periodic Boolean operations to quickly do union or intersection on meshes. The idea here is we just propagate transformations down to leaves. So it's not blocking any of the other simplification. And then we maintain a normal form. Basically, you do union or intersection of a bunch of meshes, and then you subtract a bunch of other meshes from them. These are the rules. They are actually quite simple. So you store the transformation here, you propagate down until you get the atoms, and then you apply them. And this just compose the transformations. And for this rule, I have examples. So for example, here we have the simplest case, which just flattens it into a variadic union. And then if you have some negative operands, for example, A minus B minus C union D, you just combine those negative operands. So this is why we have this this normal form. We collect both the positive and negative operands. And then if you have positive operands, you can put them to the positive part. So this is quite simple. And we have to be a bit careful when we have shared nodes. So because users may sometimes write in a manner that have shared models in between. So if you directly apply the rewriting rules, you essentially duplicate the tree. So while this is faster for each individual query, in combination, you get duplicated work. So we just check the reference count and we stop the propagation when we reach shared trees. And then we collapse the tree and then we evaluate it into a complete mesh. And then we continue with other evaluation. So there are multiple ways to optimize arithmetic Booleans. So the first way, simplest way, is we can compose disjoint meshes because union of disjoint meshes basically doesn't require any work if you are doing like half-edge data structure. And then you can also optimize it via some heuristics. For example, we can do smaller meshes first. The idea is to hope that if you combine or intersect or union those smaller meshes first, you get a smaller result, which is kind of like optimizing matrix multiplication. You want to do the smaller things first. And also you can parallelize these Booleans. So our actual Boolean routine has internal parallelization, but they only trigger for large enough meshes because we have like a certain chunk size heuristics. So if you are not reaching up to that chunk size, you are not triggering the parallel path. And also, even if you reach that chunk size, you may not be using all the cores because it's not efficient to do that. So so these are the two unrelated to computational geometry optimizations. And note that a naive implementation may cause data race. So if you consider an implementation by like having a shared heap, which orders the meshes by their size, the number of faces, and then you have a number of workers that take pairs from that heap, compute it, throw it back, and then continue. This will lead to data race because your computation operands depends on how fast the workers actually finish their work. So we need fixed size batching. Basically, we set a fixed constant k, for example, to 4, And then we take 2k smallest meshes from the heap. And then we run the Boolean in parallel. And then at the end, after all the threads finish, we put them back to the heap. This eliminates data race, but also it is slightly inefficient because you are essentially waiting for the slowest Boolean in this to complete. So I'll give two simple example timing because we haven't really do any very rigorous benchmark with this because we know that it is faster by some examples. So these two models are from the OpenSCAD PR, which integrates manifold as its new experimental backend. So this is, we call it cube with dense. It's not exactly a cube, but you are subtracting a lot of spheres from the underlying cube. And the other one is a maze. So this is a union of many tubes. So this is the negative part of the maze because outside that you have a tube, you have a cube, and you subtract this negative part from it. If I directly show the maze, you just see a cube because all the tubes are internal. So I disabled various optimizations and tried a bad evaluation order. So this green line is like the normalized running time when you have no optimizations. And if you disable the disjoint union operation, but still enable some of the rewriting, let me see. Yeah, so by default, it is the blue line. So we enable everything. So for the cube with dense, because it's like a relatively simple model, so it is just 4 times faster. And for the maze one, I remember it's like 50 times faster if we enable everything. And if we disable disjoint union, it becomes a lot slower because especially for the maze model, because most of the tubes are disjoint, so you can optimize a lot from that. And then if we change the evaluation order to a pretty bad one, for example, we are currently unioning the negative operands first, and then we subtract it from the positive part. But if we change it into keep on subtracting, then it can get pretty slow, like slower than without any optimization. So here's some of the future plans. So we plan to do some dynamic rewriting because currently our assumption is that subtraction is more expensive than union, which is generally true when you start from a relatively simple model and then keep on subtracting from it. But in some cases, you may have a very complicated model, and then you try to do subtraction to remove the complicated parts. And in that case, subtraction is actually faster than doing a union on the negative part first and then do subtraction. And we are also trying to do more lazy evaluation inside the actual implementation, like in the C++ part. This is pretty horrible to do, but we already have a few PRs that got better performance from this. And then we also want to support constraint-based modeling, which is you can define constraints between features, and then you have a solver to solve those constraints and then convert it into a model. And there's also more work on the geometry side. So I still have some time, so I guess I can do a demo. Yeah, so we basically have this like TypeScript demo. So our library is written in C++ and it compiles to WebAssembly. The parallel code is disabled here. So this demo, this web app has actually a lot of work done into it. It actually pulls from NPM for some of the scripts, but basically. Yeah, so this is the very simple model. So we have a cube first, and then we subtract a ball from it. So if we actually comment this subtraction out, it just gives a normal sphere, and then this gives a new result. So yeah, this is kind of the example from the first page, but this is truncated. Sorry. Okay. Yes. Let me see. Trim by plane. Set properties. I think I still need it. Yeah, so yeah, this removes that trim pipeline. Basically, most of this is just like very simple API, and we just push a bit to make them know that doing lazy evaluation and then do AST writing can make things go faster. So this is the end, and feel free to try the demo. It kind of works on mobile. I'm happy to take any question.